Hello everybody, today in this video I'm going to show you guys how to design this kind of T-beam, and there's slab resting on this section, this part, and actually it is looking like this. Let's say this is looking like this. There is beam and slab is resting on it, and there is load coming on top, and there is certain loading, bending and shear force due to the load on top, and also the shear force and bending due to the slab force coming to the projection area, this area. So now let's start design. For the properties, concrete is safety factor. If it's designed in Finland, that it could be 1.35 as well, but now at this moment I've taken 1.5 to be in accordance with the Eurocode, and for steel it is 1.15. Like I said earlier, concrete can be 1.35 in Finland, and 1.1 can be steel factor in Finland, but in general case, according to Eurocode, it's 1.15. and this is concrete properties. If we select 35, it changes all the values according to that, and all the values for concrete, steel and everything, safety factor, they're all coming straight from the Eurocode. And for steel I've selected A500, that means the capacity is 500 Newton per millimeter square. Now I've assumed the length of the beam is 7.53 millimeter, breadth is 4.8 millimeter, height, and there is concrete cover, and the main reinforcement is 20 and number of them is 8. This is just the general assumption. Stair reinforcement is 10 millimeter, and the distance between stair reinforcement is 2 millimeter. Definitely I can change it if this does not satisfy, then I can put it 150 millimeter or increase the reinforcement diameter, but at this moment I'm not doing anything. And a diameter of beam in reinforcement is 10 millimeter, and number of tension reinforcement is 6. So let's go further, and this is the measurement of this section over here. I've assumed this is 150 millimeter from here to here, and TV, that's the chin height of left side over here, and the picture shows it's symmetric, but I've calculated it in a different way, even 3D views, but I made it so it's symmetric, but it's not in our design. TV is 580 millimeter and TO right side is 340 millimeter, so there is a small deviation, but that is calculated in the stitch chart, so don't worry about that. And main reinforcement left chin is 10 millimeter, and the distance space is about 100 millimeter, and right chin is 10 millimeter, and distance is 1 millimeter. And this is the main loading is 93.34 kilonewton per meter, and that gives us the bending moment, which is 663.437 kilonewton meter, and shear force is on the two side to edge of the beam is 351.658 kilonewton, and this is shear force on the chain and shear force on the chain. Like let's just quickly show you. There is one shear force going down at this point if it's the support point, and there is another shear force because of this slab is going from here to down. Yes, these are two, and bending happens also the same, bending due to this force over here and bending due to this force over here. So there is two different, they are going in two different directions. So let's go to do the bending calculation first. D distance is the distance from top of the beam to the center distance, center of the lower tension reinforcement, and that means total height minus concrete cover, which I have assumed to be 35 millimeter, and the diameter of the reinforcement divided by 2, because we need the distance from center. That means TW is 20 millimeter divided by 2, it gives us 10 millimeter, and all these values are coming straight from the table. I've shown this table somewhere in the previous videos, so These are coming from table, don't worry about this value over here. And mu value can be calculated like this is the bending moment capacity of the beam divided by width of the beam times d. We just calculate it over here, and to the power 2 times FCD, it's concrete properties. It gives us 0.113, and it has to be less than 0.358. This secures the yielding happens. This secures the yielding on the main reinforcement. Once that is okay, then we can go further. We can calculate beta value. It is looking like this. Once we have the beta value, then we can calculate the lever arm, which is looking like this. Once we don't know the lever arm, then with our reference bending moment, which is design bending moment, we can calculate the required area of the steel. Because if we consider of taking bending on the concrete stretch block, then the bending due to the force in the concrete section will be 0, so moment will be equal to area of a steel times the yield capacity of steel divided by those safety factor. It will be 500 divided by 1.15, and then times Z is the lever arm, and this times this should be equals to the bending moment. And once we rearrange the equation, then we get area of steel should be moment divided by FYD times the Z lever arm, and then we get this area. This is the required area according to our calculation, but there are similar a few conditions. Area minimum required area is looking like this and this, and once we have all of them, the applied area would be maximum out of them. That means area required is 2205 millimeters square, and we've applied 8 of them. I will just change that to this value, so we are not using a number. This is 8, and TW, I just put this value because if I change the number above, then it automatically changes as well. This is done in MATCAD, and if I have to design this kind of beam and I just put the value, and then it gives me the results automatically. That's why I just put this kind of rather than putting the numbers straight. And once we know the area required according to bending moment, then we can compare that area with the required area, and if this area is more than the required one, then it is okay for bending. But then at the same time we have to do the check for shear. K is the value calculated like this, and it has to be less than 2, and this is calculated like this. Normally this is always 0.12, since Eurocode has certain values for this. It is 1.5, but if we are doing design in Finland, this value might change, and the steel ratio is looking like this. Area of required steel divided by breadth, and D is the height minus the concrete cover minus the half of the reinforcement diameter. Yes, and it is looking like this. Once we have all of them, we can calculate do the shear capacity calculation, and it gives us 188.369 kilonewton, which is way too less than the capacity required. And if we put this kind of condition, this tells me shear reinforcement is required. Now we go further to calculate the shear reinforcement, and this is 1 if it's not brace-stressed reinforcement. Brace-stressed, then meanwhile this is 0.6 if it's less than 60 MPa, and then VO max we can calculate it like this. And once we have the value, this is okay for our design. And once we have that, then we can calculate further the reinforcement area, shear reinforcement area, and after having the area, we can calculate the center to center distance for the shear reinforcement, and it is 308.653 millimeter that is less than what we have applied. If it's not less than applied, then we have to do the redesign of this small section, stair reinforcement section. But in our case, it's okay. So far we've done the bending check and shear check, and in shear check we have realized that we need to have additional shear reinforcement, and we applied the additional shear reinforcement for the beam. Now we go to chin, which is there are two sides, nosing in two sides, and now first we go to the left side. Left side we have bending moment. We have to consider slab for 1 meter, and effect of that 1 meter would be this is the distance, and force times the distance is here. So once we have all of that, then we get the bending moment, which is 3.287 kilonewton meter, and shear force is same as what we have given earlier, because that was calculated for a meter. I will quickly show you. This was here 21.910 kilonewton meter. Yes, and let's go down, let's go down, let's go down, let's go down. Yes, here. And now D is total height minus concrete cover and minus this divided by 2. In fact, give me a sec. Divided by 2. Now it is looking like this. U is this, and again we have to do this check to make sure yielding happens, and this is considered for 1 meter distance. That is why it is BP is 1 meter. And once this is we know this is less than 0.358, then we can brush it further, and beta value left side is looking like this, and Z is looking like this. Lever arm left side, definitely that is also the required area. It's looking like this, and once we have that required area, then we can calculate the reinforcement ratio, and reinforcement required minimum for 2 different conditions. And then once we have that, then we can compare that reinforcement, and maximum out of them is the required reinforcement for our chin, and it is 544.056 millimeters square. Once we have that, then we can calculate the space, which is 280. This tells us that we must have we cannot go more than this, and if our space is which we have applied, this is applied one, is less than the what we just calculated, then it is okay. In that case, the bending check is done, and then shear check. Give me a check. Yes, bending check is done, and for beam right side nosing design, this is for another side, and this also has all the moment and everything, and it is exactly the same as what we just did before, but I will show you quickly. Moment is 8.5 because this has bigger load than previous one, and this shear force is bigger. Before it was 21 point something, and D is like I showed you, and this must be divided by 2, and we get it like this. And B is this is designed for 1 meter, so it is like this. And once we get this, we have to make sure it is less than this to make sure yielding happens. And then B right, it is calculated like this, and Z is the neutral lever arm. And once we know the lever arm, then we can moment equals to area of steel times the capacity, yield capacity of steel times the lever arm. Yield capacity is here, and lever arm is here, and then we get the area, which is required area is 65.33 millimeter, and we apply the condition minimum required area, and once we have that, we take the maximum out of them, and it is 302.25. This is the required, and once we check it again, then we get the required space is 519 millimeter maximum, and that is what we have applied is less than this one, so it is okay. And this is for suspension reinforcement check. That means the tension on the reinforcement due to the shear force These are the stair force are applied left and right, and this is the calculated for 1 meter distance. This is center distance, and this is area of reinforcement. That just there is 25.019 MPa, and it should not exceed the this stress what we have just calculated should not exceed the yielding capacity of reinforcement. If it goes be more than this, that means uh, the bar will the tension capacity is more than what it tension goes more than what the capacity is. In that case, we have to do increase the reinforcement. Now so far what we have done is what we did in this design is, first we took this kind of beam. We did not consider initially, we did not consider this two slab. We just considered the load coming on top of it, and the bending. Due to that, we just did the bending check. Bending was 662, and we applied all the equation, and then we got the capacity, required capacity and area of steel is what we have applied is less than what is more than what is required, and we did the shear check, and shear reinforcement was required, and we calculated shear reinforcement rotationally, and the beam longitudinal section through beam was done, and then we did the same procedure for left nosing and right nosing. We got the bending moment, but we did not calculate the shear force. Instead, shear force in that, but we should have done that, but we have not done that. But it's no big deal, because we just can follow the same kind of, you guys can follow the shear check same procedure like over here. Yes, shear check. If it's not shear reinforcement is required, then we can go with this kind of calculation again. Thank you. If you have any question, please write me on the comment section so I can answer your question. Yes, thank you very much.